Hi, welcome to the analysis, design, and simulation of a forward converter. This is part one of a series of videos. And before I start going through a forward converter, I want to point out that the forward is actually a buck. Okay. And it's a buck that has a transformer, so it has isolation. Okay, so basically the input and the output, the grounds are separated, so you have what you can call a galvanic isolation. Okay, so in learning about the buck, how it works, you actually will know how a forward works. Okay, so I'm going to start with a buck and go through some of the derivation or the analysis, show the technique, and then we'll do the same once we get to the forward. Okay, so the buck happens to be a very popular converter, and typically it's used, or actually it's always used when you're going to do a step down. Okay, and typically with the voltages that are very low now for these microprocessors, I believe 1.2. There might be some lower. I know that we use 3.3. Okay, and if your input voltage is, let's say, from a battery, let's say 9 volts, and you want to convert from 9 to 12, well, if you use linear circuits, okay, say if you use a linear circuit, let's say 3-terminal device, where we're all seeing those chips that have 3 legs. I think it's the 78 series, like a 7805 and so forth. You have an input pin, and then you have an output pin, and then you have your ground. Typically, when you use these, let's say if you're going from 9 volts to, let's say, 3.3 or some other voltage, you end up wasting a lot of power. Okay, and typically because there's a pass, you can think of this, the MOSFET that's internally as a pass device, and it typically can be modeled as a resistor. And if you have quite a bit of current going through there, then the delta voltage, in other words the delta coming in and the voltage out times the current, will give you the power. Okay, and typically when you have linears, they're going to be very, very wasteful. Okay, so one of the reasons the buck is in use is because you don't have those inefficiency. As a matter of fact, they're very efficient, very high, typically in the 90%. Okay, so typically those are the ones that are used in all your probably phones, cameras, and so forth. They have a little buck converter in there. Okay, now here's a buck schematic, and the circuit is actually simple. You're going to have your input voltage source, and it would be a DC volt. Okay, and then you're going to have a switch. Okay, and that can be either be a BJT, a bipolar transistor, or it can also be a MOSFET. Okay, so right now I'm just modeling as an ideal switch, just to get the idea across. And it does have a second switch, and typically this would be the second switch, but instead of using a switch, we can use a diode. Okay, and in some very, very high efficient, you can actually put a MOSFET, okay, across here, and that would be a synchronous rectification. Okay, so but that's a little bit more, something a little bit more advanced, and I'll probably cover it later on when I discuss synchronous rectification. Okay, and then you're going to have your inductor and your output filter. So this is really a low pass filter. Pass filter. And then you're going to have your load. Okay, and basically that's it. Okay, so how do we analyze this? Okay, so basically when we're going to analyze, we're going to do three things. We're going to break the circuit into what I would call the on state. The on state is when your main switch is on, and then the off state is when the main switch is off. Okay, so we'll break into two circuits, on and off, and then we're going to write an equation that will describe the on, and then also a set of equation for off. And typically what we're looking for the equations that describe the voltage across VL from there to there. Now notice that I have a little dot there, so this is my reference. I'm going to use this as my positive reference when I describe VL or write the equations. This is the reference point. Okay. Once we have the equations, then we can use the volt-second rule, okay, to derive the equation. And basically the volt-second rule says that at steady state, the voltage across an inductor has to average to 0 volts. Okay, so we'll be applying this rule to actually derive a transfer function. In other words, we want some kind of a function that if we have Vn, okay, and some kind of a function here, let's say we'll call it Vx, that whatever Vn, you end up with a V out. Okay, something like that. Anyway, now before we do that, let me go ahead and define a couple of variables. Okay, we're going to define duty cycle, time on, time off, and T period. Okay, now the T period is very simple. T period is actually 1 divided by the frequency. Okay, so typically you're going to be switching this MOSFET, or your ideal switch, you're going to be switching it on or off at a certain frequency. Okay, so that frequency determines your time period, or what I call TP, or T period. So TP is the period, is going to be 1 over the frequency. Okay, now when you look at it, or when you look at graphical representation, you'll have a waveform that looks like this, where this could be the on state, which is right there, and this would be the off state. Okay, so once you have one cycle, or one cycle is actually TP. Okay, so it's the time from here to there. That would be your TP. And that, to find that, like I said, would be 1 over the frequency. Now time on would be this period, the time where the switch is on. Okay, and another way of expressing that is, in power electronics, they like to use, once TP is defined, they set this to TP. Let me remove that. Since TP is the time duration from over to there, they can say that this time period at this time is TP. So they can also say that the period here is DTP. Okay, let me go ahead and officially define that. D times TP is actually, it's a ratio. It's the ratio of okay, looks like it's locking up. Okay, there. Sometimes it freezes on me. Okay, the duty cycle is the time on divided by the time off. Okay, so that would be the ratio of that two times TP. So that would be the times ratio, and we'll define it a little bit more clearly. Okay, so time on, we can say that it's the duty cycle, D, times TP. Okay, so that's the definition that I will use. And then time off would be this period. That would be time off. And if you take this TP and you can subtract this part. And that part is DTP, so you can subtract that. So we can say that is time off is defined as TP minus DTP. Okay. Now if we take it a little bit further, we can go ahead and factor the TP, right? So you end up with that. And usually I write it in this format with the time period or the duty cycle part in front. So that's my definition for time off, and here's my definition for time on. Okay, so you can also say that the ratio, well, we'll leave it at that for right now. Okay, actually the duty cycle this is incorrect. Okay, the time on duty cycle is not time on, it's actually TP, time period. Okay, so it's actually, you can do this, you can say that T on is D times TP, and since the time period is TP, it's D. So I'll use D to define that it's the time on divided by the time period. So that's the correct. Okay. So now once we have that, we have those definition, we break up our circuit. Okay. And perhaps I can explain this a little bit. Maybe if I can zoom out. Okay. 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 See if that makes sense. So when the switch is on, you're gonna have a short across. Okay. And what it does is going to put V in on the left side of the inductor. Okay. And then eventually at steady state, the right side will be at V out voltage. Okay. The diode, since it has a positive voltage, is off, so you can disregard that. And of course you have your capacitor and your load. So that would be that schematic. Okay. And at time off, when the switch opens up, okay, the inductor reverses and it becomes a negative and positive, and because this node goes to negative, it turns this diode on. So this diode turns on and it forms a short. Okay, so basically that's open, so all of this is disregarded, and then you only have this circuit, which is an inductor whose left side is grounded, and the rest of this circuit is being charged or being supplied with the inductor. So now that I've explained that a little bit, okay, let's go here. Okay, so now from the previous development of the equations or schematics, we said that T on is D times TP, and then T off is 1 minus D times TP. We define them here. Okay, so now we're gonna use a Kirchhoff's voltage law, and we're gonna take the voltage or the KVL around this loop. Okay, now this is the positive side, so if we go this way, we see that we have a negative a negative Vn, because you're leaving the negative, and then when you come over here, you should be leaving a positive, so you can say it's VL minus Vn plus V out is equal to 0. So we have our first equation. Okay, we do the same thing here. Okay, so going in this direction. Okay, this you can neglect. There will be a 0.7 a negative 0.7 volt, but we'll go ahead and neglect it and assume that it's a short. So if we go in this direction, we see that it's a positive V out. Okay, so the equation would be VAL plus V out equals 0. Okay, so we solve for VL, so you end up with these two equations right there. Okay, so now if you were to graph this, okay, you would see that VL, the voltage would go up, and then it would reverse, and it would come back down. And let me change this, make it a little bit more consistent. We're going to say that it's Vn minus V out, and this would be V out. Okay, so now you have this waveform that describes the voltage across the inductor, and during this time, that's your T on, and this would be your T off. So during that time it would be dTs, and during this time it would be 1 minus d TP. Let me TP. Okay, so that would be that. So now we're going to use the volt second rule that states that the average voltage of the inductor at steady state is equal to 0. Well, what does it mean? Well, a way of thinking that you can think of it is that the area of this section is going to equal the area of that section. That's basically what the rule, the volt second, is. It's a graphical representation. Okay, so with that being said, then you can set an equation. Here's your volt, and here's your second, the time, which is d times Tp. Here's your volt, and here's your second, volt second rule. And when you write the equation, this is during the time on, this is time off. So basically, time on and time off, these two products, they have to equal 0. Okay. Now, if we go ahead and do a little bit of the math or the algebra, I went ahead and multiplied it out. Okay. And what I'll do is the V outs, I'm gonna move them to I'm gonna change them, flip them to the other side, and then flip it around, and you'll see what I mean. So I'll change this to a positive P. I'll change that to a negative, positive. Let me see. Yeah. And this will be a negative. Okay. And we'll say that this is Vn dTp. And if I factor V out and actually factor Tp, I should get a, let me see, should be a D, and should be a 1, and should be another D, negative D. Okay. That cancels that. TP cancels. So basically you end up with V out is equal to D times Vn. And we already said that D can also be expressed as time on times the time period, or you can say that it's D TP TP Vn. Okay, of course the TP's cancel, but that would be an expression, or it would be the transfer function. Okay. So that's how you develop the transfer function. So now we're going to do the same with a forward converter.